All right, let's get started. So in this video, we would like to talk about solar cells or photovoltaics. Uh, Solar cells are very important in our life today because they are replacing the fossil fuels for energy needs. Fossil fuels like petrol and diesel are very, very polluting to the environment, and we would like to go to renewable energy resources. And photovoltaics or PV is a very important component of the renewable energy. Okay? So solar cells are not very new. They have been there for a long time, almost 40 to 40 years or so. They were used in the satellites or space applications in the 70s and 80s. The reason is, in those applications, we don't really care about the cost. Initially, the cost of the solar cell was very large, but slowly with the progress of silicon technology, the cost of the solar cells has come down, and now we can afford them so that we can even easily install them on the rooftops and things like that. So there are a couple of images. So the first one is of the International Space Station. The arrays that you see here, these are panels of solar cells. So they're large arrays, about 74 meters, as mentioned in this caption, and they generate about 62 kilowatts of power, which is a very large amount of power. A typical home might have about 5 kilowatt of power. So about 12 times larger. So it's a large amount of power that we're generating. And because you need to run the space station and you need this much of power, okay? There's no other source there in the space. So this is in the space application, and even on the land, you have now big solar farms coming up all across India actually nowadays already. So we have, this is a picture of a solar farm which is generating about 72 megawatts of power. So these solar cells are now very important, and we would like to understand them. The fundamentals of it we'll understand in this lecture. So when we think about solar cells, the first important feature that we need to understand is the solar spectrum. So sun is generating a lot of energy. You see that, right? So it generates heat and light. So if you look at the spectrum of the solar radiation, it looks like this. So the picture in yellow is the spectrum of the solar radiation. You see that the radiation is from 250 nanometers to about, in this case, I'm only showing 2.5 microns, but typically it can even go up to longer. The intensity falls. You can even have up to 4 microns or so, but the intensity falls rapidly. So this is a solar radiation, and we say that sun behaves like a black body. You might wonder, why black body? So in scientific terms, a black body is a perfect absorber of radiation. It absorbs all wavelengths with equal intensity. And if you heat up a black body, it will emit all wavelengths with equal intensity, or rather, a very large efficiency, basically. Okay. So here you see that if you have a black body, there is theoretical analysis for that, and essentially the solar spectrum is behaving as if it is basically a black body heated up to 5,800 Kelvin. So that's why we say that the solar temperature is about 6,000 Kelvin typically. So because of that, you have this peak energy in the visible part. So you see this radiation, in between 300 to 700. Between 300 to 700, we call it visible range, 300 nanometers to 700 nanometers. Only this is what we are seeing, and because it has all of these wavelengths in almost equal intensity, you see that sun is whitish in color. Okay. And but you still have IR radiation, which is extending up into longer wavelengths. So this is basically the IR radiation, infrared. Okay, infrared means beyond red. So in the 600 to 700 nanometers is the red part of the spectrum. So beyond red is an infrared, and in the lower wavelength part, below 300, is called ultraviolet because below violet. Okay. So that's the terminology we use. And if you're not familiar, you should just refresh this part. All right. So now when this solar radiation is incident on Earth, the yellow spectrum is what is measured outside, in the space. But the red part is what you get on the ground. The red, this is spectrum on the ground, or that's why it's saying sunlight at sea level. So what you see is there are certain, of course, there is some absorption in the atmosphere. Okay. Absorption of all the wavelengths. But mainly in the visible and blue part of the spectrum, there is more absorption. And then in the IR also you see some bands. Okay? These are IR absorption bands corresponding to various molecules. For example, if you have water in the atmosphere, which is there, right? I mean, the water vapor is there in the atmosphere. That will lead to some absorption, a specific characteristic absorption feature set around, this part, this part, and then the harmonics. And then there is nitrogen-related absorption and other things. Okay, there are a lot of molecules or gases which will absorb. So because of that, you see at certain windows, you have complete absorption, and other wavelengths it is transmitting, and you see nearly almost all the solar radiation is reaching the Earth. So this is about the solar radiation, and because at each location the solar radiation is different, and depending on the latitude, longitude, it will vary. The amount of intensity that reaches Earth will vary. So scientists adopt a very standard spectrum, and usually we refer to it as a solar spectrum AM 1.5. What this means is AM stands for air mass. It's just a notation saying that it is amount of radiation that is absorbed when sun is at roughly 45 degrees of angle. Okay, so that's a standard spectrum we refer to, so that people can compare with solar cells performances in different locations. Okay, and it turns out that if you have AM 1.5 spectrum, if you sum up all the intensity that is available at all wavelengths, the total will turn out to be about 100 milliwatts per centimeter square. Okay, this is the intensity of AM 1.5 spectrum. So this is the total amount of power that is incident on the Earth. Okay, at a typical, let's say at a 45 degrees angle on the surface of Earth. So this is what we have, and now how much of it can we harvest? That is what is important for us. Now, when we build a solar cell, we would like to harvest as much energy as possible from here. Okay. To understand that, of course, we need to calculate what is known as, we have intensities that is given to us. Okay, but we would like to calculate the number of photons that are incident. Okay, and that is going to depend on each wavelength, because you see, we've already seen that the photon intensity is dependent on the energy times the number of photons, right? So if you have a higher energy, then you will have a lower number of photons. And also there is this feature that we call a spectral irradiance, which is the amount of intensity at each wavelength per centimeter square. Okay. So the expression that we use to calculate that is given here. So F lambda, which is the total irradiance, is equal to the flux. So this is phi is the photon flux, and E lambda is the energy of the photon, and 1 over delta lambda is just the window, in that particular window, how many photons are incident. Okay, and for making these calculations, typically we use them in micrometers. So the F lambda we take it in micrometers, and delta lambda we take it in micrometers, to make sure that there is no error. Okay, so if you look at this, the number of photons turns out to be about 10 power 17 photons. Typically, if you take, let's say this is, I would say, around 0.5 micrometers. If you take 0.5 micrometers, roughly about 5 into 10 power 17 photons per centimeter square per second. All right. So this is a peak. So which of these photons will be absorbed and which will not be absorbed, right? So we know that, let's say, if you take silicon has a EG of 1.12 EV, right? So let me put the EG of silicon here. So let's say somewhere here, approximating it. So if your photons are having wavelength higher than this number 1.12, oh sorry, this is 1.12 EV. Well, I should actually do a calculation. So lambda in micrometers is going to be 1.24 divided by 1.12. Okay, EV. That will be roughly about 1 micrometer, roughly 1.1 micrometer maybe. Okay, so yeah, I mean, I'm nearly there. Okay, so in lambda scale also it's 1.1 micrometer. So if the wavelength is larger than 1.1 micrometer, so if the wavelength is larger here, this is not absorbed. Lambda greater than 1.1 micrometer, is not absorbed by silicon, right? So all of this intensity that is there, the photons that are there at those wavelengths are not really useful to us. What is useful for us? If you are building a solar cell out of silicon, we can only absorb this range of wavelengths, okay? Lambdas that can be observed, that can be absorbed by silicon, okay? So I'll come back to it. That's why I'm spending some time on this. I'll come back to it and then explain how, uh, how to choose materials. When we talk about the efficiency of solar cells, we'll come back to this spectrum and understand this in greater detail. Okay. So I'll give you a problem in the assignment on this. So essentially, you could take, if you take the spectral irradiance, and I'll give you some numbers. This would be something like, we saw this in the first graph, right? This is, well, this is at AM 1.5. If you take AM 0, or okay, if you take the irradiance outside, in the space, it's roughly about 2 watts. 2 watts per meter square per second at, let's say, typically, let's say it's 500 nanometers, okay, or 0.5 microns, right? At 0.5 micrometers, it's just take it this way, and then try to compute what is the number of photons, okay? And essentially, what you'll have to do is use it in, okay, this is also, if you go back and look at this units is watts per meter square per nanometer. So what we'll have to do is, I'm sorry, since I said watt, there should not be a second. That's a mistake on my part. This should be nanometer per nanometer. Okay. So we would like to use it in the units of the micrometer. So I'll write this as 2000 watts per meter square micrometer. Okay. So the flux, photon flux phi is going to be this number, 2000 watts per meter square micrometer, divided with the energy of the photon. I said it's 500 nanometers. So if you take 500 nanometers, this is going to be 1.24, which is a denominator, divided by 0.5 micrometers. Okay, this is the energy of the photon. Energy of 500 nanometer photon times delta lambda, which is going to be 1 micron here, okay, and divided by, so I don't have, in micrometers I have to mention this, so I don't need, I just put 1 there, delta lambda, and then divided by into 1 by 1.6 into 10 power minus 19, okay. So with this, you should be able to compute the number of photons, and I'll leave it to you, but in the assignment you can verify that it will be typically in the range of 10 power 17 or so. Okay, so I'll leave that to you. Please do that as part of the homework. Okay, so these many photons are incident on the semiconductor. So how do we convert into electricity, right? So that we can do by using a PN junction. We've already studied PN junction in great detail. So let's say you have this, P and N regions, and then there is this IV characteristic that you get for a PN junction, correct? But if you shine light on this, what will be the what is the amount of current that is generated? Is there any current? Let's start with a simple piece of silicon. Okay, I shine light on it. Will it generate current? Right? Well, it does not generate current. The reason is, if you shine photons, you're going to generate electron hole pairs, but they will recombine, right? You're only going to create a certain excess of minority carriers, but you're never going to cause them to move, right? On an average, because if you, let's say, assume uniform illumination, you're going to generate a uniform excess minority carriers, right? But you're not going to generate current, right? So this is not suitable because recombination. You generate electron hole pairs of EHPs, right? You're essentially shining this with photons. If you assume uniform illumination, then you'll essentially just generate, and then they'll recombine, and there'll be steady state some excess minority carriers. All right. So if you want to really extract that current, you need a device which has certain field. So you can generate electron hole pairs and then they should be swept away. And that is what is, that's what happens in a PN junction. That's why we use PN junctions for solar cells. So let's say I have my PN junction this way, and there is a depletion region here, right? There is a minus and there's a plus. This is P type, this is N type. So we know that the electric field in this PN junction is in this fashion, right? In this direction. So now if you shine photons, what happens? Okay, if you have quasi-neutral regions, right? In quasi-neutral regions, no current. No current. Why? Because there is no field. There's a very, very tiny field. It doesn't really result in current. But in depletion region, if you shine light, whatever light is incident on that, it will generate electron hole pairs. So let's say it generated electron hole pair. Immediately, the hole will move towards this direction. Hole will move in this direction. Electron will move in this direction. And so they will separate out in terms of they form current. Okay, so this generates current flows in external circuit if it is there. Okay, so that's what happens. So how much is this current? Okay, let's try to estimate that. Let's say I take instead of directly using the solar spectrum, let's assume that you are shining a 1 milliwatt laser. Okay, let's say we use a 600 nanometer laser. Okay, or 630 probably is better. Okay, let's say 630 nanometers laser with 1 milliwatt of power. I'm saying laser because laser has one single wavelength. We don't have to worry about various wavelengths. Okay, so if you have this laser, how many photons are there? Well, you can compute how many photons are there, right? Because the this is power 1 milliwatt is going to be number of photons n lambda times energy of the photons. Okay, so this is going to be number we can compute how many photons are there. This will be 1.24 divided by 0.63 in micrometers. So that will be the, okay, they should also be 1.6 into 10 power minus 19. Okay, so with this you can compute. You will see that if you do this calculation, you will end up getting something like 10 power 15 photons per second. Okay, if you have a laser which is having 1 milliwatt of power, roughly, I mean, it will be 2 or something. We don't really need to care about the order of magnitude will be 10 power 15 photons. So if you have 10 power 15 photons and they are swept across the device, what is the amount of current that we generate? Just a moment. I'm sorry, there is a short interruption. Okay, so yeah, when you shine this 1 milliwatt of laser, you'll get about 10 power 15 photons per second. So how much current is generated? Well, to calculate the current, we know that, essentially there's an electric field and that is going to cause drift of these carriers. Electron hole pairs are generated and they will drift across the depletion region. So the current is going to be J drift, right? Is going to be N times E is a charge, mu times mu into electric field, right? So we don't really, I mean, if you know the electric field and the mobility of the carriers, you can compute. But this number N is going to be 10 power 15, okay, photons per centimeter cube, okay, and this is going to be charge, this is going to be mobility. You can compute 1.6 into 10 power minus 19, and typical depletion voltages would be 10 power 4 volts per centimeter, and mobility, let's take it to be 400 centimeter, 400 centimeter. 400 centimeter square per volt second. Let's try to, you can compute it. You can see how much is the current that flows in a PN junction. You will see that it is, 10 power 15 and 10 power 19, so 10 power 4. So roughly it will be, few milliamps per centimeter square kind of current. Okay. So what happens is just by shining light, you are getting current, in the range of maybe milliamps or hundreds of microamps. That sort of a scale you should get currents. So, hundreds, maybe hundreds of microamps to milliamps, of current per centimeter square. Okay. So if you have that, you see what's happening. So when you shine light, you are essentially increasing the current in the reverse bias. Okay. When it's in the forward bias, it's anyway going to be dominated by the regular current, but you are essentially causing in the reverse bias, there was this saturation current before, right? This is reverse saturation current. But when you shine a light on a PN junction, the reverse saturation current increases. Okay. So this is basically light, IL, I'll call it, current due to light. And if your intensity of light increases, you get greater amount of current, right? So as you increase light intensity, the current increases in this direction. Okay. So you have more and more current that flows because of light. Okay. So this is very useful for us because we'll try to calculate the characteristics of a PN junction based on this. Okay. So now, yeah, the same scenario. Let's say you have a PN junction, simple PN junction, and you shine light, and there is a resistor across the PN junction. You connect it across a resistor. So when you shine light, there is a current that flows in, right? So the direction is IL here, in the opposite direction to the regular current. It flows across the resistor. When it flows across a resistor, it creates a voltage drop across the resistor. And then you can apply the KVL, and then you can write the expression for current in this structure. What happens is, first of all, there is a current which is flowing in the negative direction. I'll call it minus IL. Okay, that is flowing. And then that leads to a bias across the voltage. I'll call it V. Okay, and that is applying across the voltage. So there should be it's forward biasing the PN junction. So this gives you a current which is basically going to be, I'll call it IS, reverse saturation current, times exponential QV by KT minus 1. Okay. This entire thing is essentially going to be a total current, I total. Okay. So basically you have the diode current plus the reverse saturation, light generated current, and that is your total current. Just taken into account the direction of the current. So there's a minus IL for this. So in terms of IV characteristic, how does it look like? Well, if you have a regular PN junction, you have this forward bias current like this, which is, above a threshold voltage, it is increasing. And if you shine light, you're going to cause a reverse current, which is kind of fixed, right? And now the total amount of current is going to be the red curve, which is given here. This is the I total. All right. So there are a few features that we have to notice here. That is, what happens when you apply, there is no voltage. Okay. Let's say we open circuit. We don't have we don't have any current, let's say. Okay. If you don't have any current in the external circuit, we short it basically. Okay. So short the cell. Okay. Let's do this. I'm sorry. Let's first case, I'll take it to be short the solar cell. What happens if you short a solar cell? V is going to be 0, right? V is equal to 0. That implies this term, this is going to go to 0. So this is going to go to 1, sorry, this is going to go to 1. So this term is going to go to 0, second term. So I total equal to minus IL. And this is this is a very commonly found scenario. We call it short circuit current. We call this as ISC. This is the term used in the solar cell community. So ISC basically means short circuit current. So you take a solar cell, short it, and then shine light and see how much current you're generating in that. Okay, that is short circuit current. The second scenario is you take open circuit. Okay, open circuit, which is I total is 0. There's no flow of current in the external circuit. So what happens? Well, you can simply rearrange this equation. So this is going to be IS times exponential QV by KT minus 1 is equal to IL. So rearranging this, we can write, we will call it open circuit voltage, VOC, is going to be equal to KT by Q ln of, 1 will go that side, so 1 plus IL divided by IS. This is called as open circuit voltage. This is another important parameter for a solar cell. So if you don't just connect the solar cell to anything and you just shine light, you're going to generate electron hole pairs, and they will be swept across, and they'll essentially give you a potential that you can measure at the edges of the solar cell. And this is called as open circuit voltage. And these two things are very easy for us to measure. And that is why there's so much of significance for this. And if you show these two parameters on a IV graph, so what happens is the open circuit voltage where the current is not flowing, this is going to be this point, right? And the short circuit current when there is no voltage across the diode is going to be this point. And between them, the IV changes, the current changes in this fashion from short circuit current to the open circuit voltage. So there is one thing that we need to note here. So if you take a regular IV characteristic, let's say here, let's say IV characteristic, this fashion, in the first quadrant, let's say this is voltage and this is current. So here, I into V, power is going to be given by power equal to I into V, right? Current into voltage. So if you have here, IV power is positive. Here also power is positive, okay? Right? That means essentially you are supplying power into the diode, okay? So whether it's in forward bias or reverse bias, that happens. But when you shine light, you are not supplying power from any external battery, but power is getting generated from the solar cell. And that is why you see that here the current is negative and voltage is positive. So power is negative here. Power negative means essentially it is supplying, the solar cell is supplying to the external circuit, to the external load. That's why this is in the fourth quadrant. Okay. So basically here, so solar cell generates power, right? It's delivering to an external circuit. So what is the range of power that you can generate from a solar cell? Well, it goes between two extremes. Power is basically the voltage into current. So when you are in the short circuit condition, you have current there, but there is no voltage. So power is zero. So here, at this point, no voltage implies P is zero. At the open circuit condition, you have no current, implies P is zero. So between these two extrema, you can have non-zero power, okay? And there will be some sort of a voltage wherein the power is going to be maximum, okay? And that is, we call it as maximum power point. At this point, maximum power point. So the solar cell generates power, and you can measure that. Okay? And we would like to operate the solar cell at that maximum power point so that you draw as much power as possible from the solar cell. All right. So what is this maximum power point? Okay. So it's very easy to analyze. So we've already seen the total current. I total is going to be minus IL plus IS times exponential QV by KT minus 1. Right. This is the total current. And power is basically going to be power P equal to I total times the voltage. So I can write that. And then I can take a derivative of it with respect to voltage to find out where is the maximum power point. Okay. dP by dV is going to be 0 at maximum power point. Right. So how much is this? Well, if you differentiate it, power into voltage, so current into voltage, sorry, this is going to be dP by dV is going to be equal to minus IL and IS into, okay, that minus IS I'll take out, so minus IS plus exponential QV by KT times voltage. So this is going to be that voltage. I'll take a derivative. So exponential QV by KT plus, now I have to differentiate with respect to the differentiate the exponential. So there's going to be plus Is into voltage times exponential QV by KT, and then I have to take Q by KT. So there will be into Q by KT. So this has to be equal to 0. That is the condition that is the voltage at which you get the maximum power, right? So if you rearrange this equation, if you have this will be IL plus IS is going to be equal to, I'll take IS common here, exponential QV by KT, and then I'll write a bracket. So 1 plus QV by KT, I think. Okay. So what this gives you is basically an expression to calculate, it's a kind of a transcendental equation. I can take out IS here. So I'll put, so 1 plus IL by IS is going to be equal to, well, it didn't really help much. Okay, it didn't help much, but yeah, exponential QV by KT times 1 plus QV by KT. So this is a transcendental equation that we are getting. So you have to substitute. Let's say you're given some reverse saturation current, and you know the saturation, the light generated, current. Then you can try to compute what is the maximum power point, maximum voltage at which, voltage at which the maximum power occurs. Okay. So if you look at the IV characteristic again one more time of the solar cell, what you saw was this is voltage, this is current. So you have a graph which looks like this. So you have the VOC and ISC, which kind of represent the limits. Okay. And the maximum power point is going to occur somewhere in between. This is somewhere here. This is going to be V maximum, and this is going to be I maximum, at which you get the maximum power. So in the solar cell community, we define one parameter which we call as a fill factor. Okay, the way we define fill factor is fill factor is equal to Vm times Im divided by ISC VOC. Okay. So I'll take the extreme. So I can imagine this thing to be a rectangle. So if I draw it in blue, this entire thing, I will draw a rectangle, my approximation of a rectangle, yes. In that, how much fraction of that is occupied? That is the fill factor. Okay. So you imagine the maximum power point as one rectangle. So there are two rectangles here. One is the bluish rectangle. The other rectangle is going to be my blackish rectangle. So how much of the area of the black rectangle compared to the blue rectangle is my fill factor? Okay. This is kind of, it tells you how good your technology is. And if you fabricate a very, very good device, you can get high fill fractions. Okay. Typically, this number is going to be somewhere between 0.7 to 0.8 for a solar cell. Okay. So this gives us a very easy way of comparing, because in the end, in the next video, I'll show you a few solar cells, and we'll also talk about the efficiency of solar cell. And when we analyze the efficiency of solar cell, it turns out that this fill factor is going to be a very important parameter. So what did we do in this video? We first introduced a solar cell. We said if you shine light, it's going to generate electron hole pairs, and they will get separated out, and that will result in some voltage across the external circuit. So it is going to deliver power to an external circuit, and that delivery happens, at a particular point which we call as maximum power point, where the maximum power is transferred. Okay, and we derived an expression. So I'll give you some problems in the exam, in the assignment. Just try to compute. Using these formulas, you should be able to compute, and then you'll get a feel of what is the kind of currents involved. All right. So I'll stop this video at this point. I'll go back and I'll In the next video, I'll talk about the efficiency of a solar cell. And with that, I'll stop the discussion about the solar cell. All right. Thank you very much. Have a great day. Bye.